Okay, get ready for a deep dive. We're tackling the chemistry of the universe today, and you've sent in some fascinating stuff about how elements were created. We've got a peek at a cocktail party chemistry episode and a whole bunch of factoids.
Sounds like you're trying to become the ultimate cocktail party expert.
Well, who wouldn't want to drop some knowledge about cosmic chemistry?
It is a pretty captivating topic.
Let's start at the very beginning, Big Bang territory. We're talking about the formation of hydrogen and helium first, right?
Exactly. The Big Bang was incredibly hot and dense, a chaotic soup of particles. Then, as things cooled down, the simplest atomic nuclei started to form. Hydrogen with its single proton and helium with 2 protons and 2 neutrons.
So all the matter in the universe essentially started from those two. Wow. But wait, if the universe started with just hydrogen and helium, how did we get all the other elements we see today? Did the Big Bang create everything?
That's where things get even more interesting. Hydrogen and helium make up most of the universe, but they can't explain the diversity of elements we find, like here on Earth. We need heavier elements like carbon, oxygen, and iron for that.
Ah, so those heavier elements must have come later.
Precisely. The universe had to have a way to forge these heavier elements, and that's where stars come into play. Stars are like giant nuclear furnaces fusing lighter elements into heavier ones. It's called stellar nucleosynthesis.
So stars are basically cosmic kitchens cooking up new elements. How does that actually work? What's happening inside a star?
Imagine the core of a star as a giant pressure cooker. It's incredibly hot and dense, reaching millions of degrees. In these extreme conditions, hydrogen atoms are forced together so tightly that they fuse, forming helium. And this fusion process releases enormous energy, which is what makes stars shine.
So stars are literally powered by fusion. That's incredible. But how do we get from helium to, say, carbon or oxygen? Do all stars create the same elements?
Good question. As a star gets older and uses up its hydrogen fuel, it starts fusing helium into heavier elements. Helium fuses into carbon, carbon fuses into oxygen, and so on. It's like a step-by-step process, building up the heavier elements. But the types of elements a star makes depends on its mass.
So bigger stars cook up different elements than smaller stars?
Exactly. Larger, more massive stars have more gravitational force and internal pressure, so they reach much higher temperatures in their cores. This lets them fuse even heavier elements all the way to silicon and iron.
So different stars create a whole variety of elements. Is there a limit to how heavy of an element a star can create?
Yes, there is. Fusing iron actually takes more energy than it releases, so once a star starts making iron in its core, it's essentially running out of fuel.
Oh, that sounds ominous. What happens when a star gets to that point?
That's when things get explosive. When a massive star runs out of fuel, it can't support itself against gravity anymore. The core collapses, and the outer layers of the star are blasted outwards in a supernova.
Supernovae, those are some of the most powerful events in the universe, right? They can outshine entire galaxies.
They're incredibly powerful and bright. But even more importantly, supernovae disperse these newly created heavier elements into space. It's like a cosmic fireworks show, scattering the building blocks of planets and life.
A star's death is actually essential for creating and spreading elements that make up everything. That's pretty poetic.
It is a beautiful cycle of creation and destruction. The heavier elements made in the heart of stars are scattered by supernovae, enriching the interstellar medium, and this enriched material can then form new stars and planetary systems.
It's like a giant cosmic recycling program.
Exactly. Elements are constantly recycled through star formation and destruction. It's a continuous process, so the universe is constantly evolving.
All right, we've gone from the Big Bang to supernovae, and it's clear that stars are like alchemists, transforming hydrogen and helium into all sorts of elements. I bet that's a popular topic at any cocktail party.
It certainly would be. But there's more to the story. What happens to those scattered elements? How do they end up forming planets and ultimately us?
That is a great question. I guess we need to dig a little deeper into that cosmic recycling program. Where do we go from here?
Let's shift focus to how these elements come together to form the planets, moons, and other objects we see in the universe. It's a story of gravity, accretion, and the birth of new worlds.
Sounds like we're in for another round of mind-blowing revelations. Let's do it.
So we've talked about supernovae scattering those seeds of new worlds. But how do those scattered elements actually come together to form planets and other celestial objects?
It's hard to imagine those tiny particles spread out over such vast distances, somehow forming something as massive as a planet. What causes that to happen?
Gravity is the key, that invisible force pulling everything together. Imagine a huge cloud of gas and dust left over from a supernova, or maybe even from the early universe. And this cloud is made up of those scattered elements, hydrogen, helium, and all those heavier elements forged in stars.
Okay, so we've got this giant cloud of, well, cosmic dust. How does it go from a cloud to a planet?
Well, within this cloud, there are little variations in density. Some areas are a bit denser than others, and those denser regions have a slightly stronger gravitational pull. That little bit of extra pull starts attracting more particles, and as more particles clump together, the pull gets stronger and stronger.
It's like a snowball effect. The more it gathers, the faster it grows.
Exactly. Over millions of years, these denser regions keep pulling in more and more gas and dust. The cloud collapses under its own gravity, and the material at the center starts to heat up from all the pressure.
So are we talking about the birth of a star, all that material collapsing and heating up until it ignites fusion?
Exactly right. But the fascinating part is that not all of the material ends up in the star. As the cloud collapses, it also starts to spin, and this spinning motion flattens out the remaining gas and dust into a disk around the new star.
Like spinning pizza dough in the air.
I like that analogy. And in this rotating disk, that same process of gravity and accretion is happening all over again. Tiny particles are colliding and sticking together, forming larger and larger clumps.
So it's like miniature solar systems forming within the bigger solar system.
Precisely. These clumps keep growing, sweeping up more material from the disk. And eventually, these clumps get big enough to be considered planetesimals, the building blocks of planets.
So these planetesimals are kind of like baby planets. Still tiny compared to the real thing, but on their way.
That's a great way to think about it. And over millions more years, these planetesimals crash into each other and merge, growing larger and larger until they eventually become planets.
So the planets we see today, like Earth, are basically the result of billions of years of cosmic collisions. It's mind-boggling.
It is, and the type of planet that forms depends on what materials were in that original protoplanetary disk. Planets that formed closer to the star, where it's hotter, tend to be made of rock and metal like Earth and Mars.
Because the lighter elements, like hydrogen and helium, get blown away by the heat and solar wind.
You got it. While planets that formed farther out, where it's colder, can hold on to those lighter elements and become gas giants like Jupiter and Saturn.
So a planet's location in the solar system has a huge impact on what it's made of and ultimately its destiny.
It's this fascinating interplay of gravity, temperature, and the different elements that are available. But there's another piece to this. What about all those heavier elements created in supernovae? Where do they fit in?
Yeah, I was just thinking about that. We've been talking about hydrogen and helium and the basic stuff that makes up planets, but what about the elements that are essential for life, like carbon, oxygen, and nitrogen?
Well, remember how supernovae scatter all those heavier elements? Those elements don't just disappear. They become part of the interstellar medium, those vast clouds of gas and dust all throughout the galaxy.
So they're basically seasoning that cosmic soup with the ingredients for life.
Exactly. When new stars and planetary systems form from this enriched interstellar medium, those heavier elements get incorporated into the mix. They become part of the planets, the moons, even the atmospheres of these new worlds.
Okay, so this is where it gets really interesting. We've gone from hydrogen and helium to heavier elements, from stars to planets, and now we're talking about the building blocks of life itself.
You got it. Those heavier elements are crucial for the formation of complex molecules like organic molecules, which are the basis for life as we know it. Without those elements, scattered by supernovae across the universe, life as we know it wouldn't exist.
It's incredible to think that the very atoms in our bodies were once part of a star, scattered in a supernova, and then became part of Earth billions of years ago. It really connects us to the universe and its incredible history.
It does. It highlights how interconnected everything is, from the tiniest atom to the largest galaxy. But there's still more to explore. What about the evolution of elements on Earth itself? How have they interacted and changed on our planet over time?
Yeah, that's a good question. We've been talking about this cosmic evolution, but I'd like to bring things back down to Earth and explore how the elements have shaped our planet's history.
That's a great idea. We can talk about how geological processes like plate tectonics and volcanoes have concentrated certain elements and created all the diverse landscapes we see today.
All right, let's ground ourselves on Earth and see how those elemental forces have shaped our planet's evolution. All right, we're back, ready to bring this cosmic journey down to Earth. We've traced the origins of elements from the Big Bang to supernovae, and now it's time to explore how those elements have shaped our planet.
It's quite a story, all those cosmic building blocks transformed and rearranged over billions of years by geological processes.
So it's Earth's own internal chemistry set, right? What are some of the key players in this planetary transformation?
Well, plate tectonics is definitely one of the most dramatic. The Earth's crust is broken up into these massive plates that are constantly shifting and interacting.
Right, like continental drift, those huge continents slowly creeping across the globe over millions of years.
Exactly. And those movements have a huge effect on where elements end up. When plates collide, they push up mountain ranges, bringing deep rocks and minerals up to the surface.
So those incredible mountains are basically the result of Earth's chemistry churning away.
You could say that. And when plates pull apart, they create those rifts and valleys, which lets molten rock from the mantle rise up and form new crust. That's volcanism, and it also plays a big role in shaping Earth's elemental landscape.
Volcanoes, they're a pretty powerful display of Earth's raw energy. I bet they have a big impact on elements, right?
They do. Volcanoes erupt, right? They release all sorts of gases and molten rock, lava, which has a mixture of elements from deep inside the Earth.
So volcanoes are like Earth's pressure valves, releasing all kinds of elements into the environment.
That's a good way to think about it. And these volcanic emissions, well, they can be both good and bad. Volcanic ash can make the soil more fertile, but it can also pollute the air and even cause climate change.
It's a good reminder that even the most powerful natural processes are all about balance. But what about those heavier elements we talked about, the ones that came from stars and supernovae? How do they end up concentrated in certain places on Earth?
Well, over millions of years, geological processes like weathering, erosion, and sedimentation have redistributed them.
So wind, rain, rivers, they're all Earth's sorting machines, moving elements around.
Exactly. For example, some minerals are tougher, harder to break down, and so they tend to build up in specific spots. And that's how we get those ore deposits rich in valuable metals.
So that's how we get gold mines and other sources of precious metals. Wow, those elements started in stars, traveled across the cosmos, and then ended up here because of natural processes.
It really is quite a journey. It shows how everything's connected in the universe. But what about those elements that are essential for life? How do they get to the right spots to allow life to start and evolve here on Earth?
That's the big question, isn't it? We've talked about how heavier elements got here, but how did they get concentrated enough to become those building blocks of life?
That's where things get even more complex and interesting. It involves geological processes, chemical reactions, and even the earliest life itself. It's all interconnected.
So it's not just about the elements being here, but also about them being in the right forms and amounts to support life.
Right, and that's where water is so important. Water can dissolve lots of different substances.
Yeah, water is the universal solvent, classic chemistry lesson.
And because it can dissolve and carry substances, water is essential for life. It moves nutrients, removes waste, and helps form complex molecules.
So water's like Earth's circulatory system, moving elements around and helping all those vital chemical reactions happen.
Exactly, and over billions of years, water has interacted with rocks, minerals, and the atmosphere. It's dissolved things, concentrated certain elements in certain places.
It's like a giant cosmic tea brewing process, with water extracting and concentrating the flavors, or in this case, the elements, for life.
I like that. And that concentration process is vital for creating the right environment for life to emerge and thrive. Like the early oceans were probably full of dissolved minerals and organic molecules, a perfect breeding ground for the first single-celled organisms.
Wow, it's amazing to think that simple water-dissolving rocks could have played such a big role in life's beginnings. It really makes you appreciate chemistry and how everything on our planet is connected.
It does, and it's a reminder that even the simplest processes can have huge impacts on the evolution of life and the shaping of our planet. We've journeyed from the Big Bang through the hearts of stars and back down to Earth, exploring the incredible processes that have created everything around us. But here's something to ponder. If elements are constantly being recycled, could atoms within our own bodies have once been part of a distant star or even another planet? It's mind-blowing, right? Thanks for joining us on this deep dive.